We're given quite a lot of words in this question, including some hints, which is a typical for these Olympiads. Doing the question without the hints or just simply doing part B can be very challenging, but like the whole point is that we're given a little bit of advice along the way. So let's look at part A. Although it's good to read the whole question, I'm going to assume you've done that, and then yeah, let's tackle part A. So Beth has this black counter and Wendy has a white counter, and they move the counters on this board. Okay, there's two boards, but the B is the other board. And given the starting positions and these rules, so each turn, each player moves their counter either one square to the left or one square to the right, if they can, that is. So the black one obviously can't move to the right, it would have to move to the left. We have to prove that the black and white counters can never be in the same square at the same time. Well, one approach to this question is to maybe talk about the first move and the second move, but ultimately you're going to have to talk about the general sort of idea. So I think it's best to kind of straight away, generalize and say what's happening. And that is the boards, the color of the squares alternates along the board. That's really important. And white, the white counter starts on black, and the black counter starts on white. Whenever they move, they will switch colors. Therefore, so I'm not just talking about the first move where obviously white will go on to white, black will go on to white. I could add that, but I'm just going to say they switch colors. Therefore, they can never end up on the same color. Okay, I feel like I've given enough information. I've said that the colors alternate, so they just can't end up on the same color. And therefore, they cannot meet. Since then, they would have to be on the same color. So I feel like this is a pretty solid argument. I've been quite general in my explanation. I've written a fair few words. Should be enough to justify 3 marks in this starting question. Hey, nice. Let's take a look at part B. So now we've got a different board. Each turn, each player moves the counter to a triangular cell which shares one edge with the cell that their counter is currently in. So the black one could move down, but it can't move over here or here. The white one could move here, here, or up. So there's going to be three positions for when it's in the kind of in the middle. When it's on the edge, it's going to depend where it is. So when it's at like a corner is what I mean. Can their counters ever be in the same cell at the same time? And it gives us more advice. Like if the answer is yes, we need to give an example of how that could happen. Just one example would be enough. And if the answer is no, then we're not going to want to look through every single possible set of paths. Instead, we need to make an argument for why they cannot. And part A gives us quite a bit of help with that because in that question the board was shaded in different colors, black and white. Here it's not, but we could shade it in. So I'm going to again have black starting on the white square, and then the only one it can move down to is this. I'm calling it a square, triangle. It can move down to here, so I'm going to change that to a different color. And when it's on this one, it could either move up or left or right. It could move to white, and then it could move to black after this. I'm just going to alternate the black and white in the same way that the first board had. Okay, so our answer starts out with color the board as shown. Um, every triangle's edges are adjacent sorry, every triangle's edges connects to a triangle of a different color. That has I say a different color, there's only two colors. So the black counter starts on white. The white counter starts on black, opposite colors. When they move, they will swap colors. And not just on the first move, but each time. Maybe I could give an example. Okay, we could go here, then here, then here, then here. Okay, so white, black, white. See example. They will therefore remain on different colors. Sorry, my writing is a little bit difficult to read, but hopefully you can hear what I'm saying. And therefore they can never meet. Essentially, I've used the same argument as in A, and when I actually wrote this on paper, I just literally said the same argument of A applies. I feel like I need to just write it out again, especially if this is a 7-mark question. But yeah, we color the board as shown. That's the bit we have to realize. Part A has given us that helping hand. Every triangle's edges connects to a triangle that has a different color, so we can never go from black to black the way I've colored it. Black counter starts on white, the white counter starts on black. When they move, they swap over colors. One example given, and they will therefore remain on different colors as they progress. And therefore they can never meet because you can't have them both on black at the same time. So I think that's enough. That is an interesting question, and interesting, a slightly different question, I suppose. Um, and the question is, if we were just given this from the start, would we realize to do that? It's a really powerful way of solving a problem. And there's questions like this using chessboards where you have to prove what what squares different pieces can move to, like a knight, what squares can it move to, a bishop, and so on, and you can make similar kinds of arguments. So, an interesting look into that sort of question.